Yes, okay. Yes, so as Hege said, I want to introduce the topic of clumped isotope thermometry, and especially its application to speleothems here. It's going to be a tale about a new, well, maybe not so new anymore, a temperature proxy that we can use in speleothems, but it's also going to be quite a lot about isotopic disequilibrium effects. So brace yourself. It's not a very straightforward tool to use. What I want to do today is the first part of the lecture will be about the basics. What is clumped isotopes? What's the principles behind it? And also just briefly how we measure clumped isotopes and where the challenges are analytically. And then the second part of the lecture is about how we apply that method to speleothems, because it's a method that's applied in many different aspects of earth sciences. But here I'll obviously focus on speleothems and show you some results that have been obtained with this method, but also talk quite a bit about the challenges and how we're currently tackling these. And these are, as I said, mainly about disequilibrium effects. So just let's jump right in. What are clumped isotopes? Clumped isotope is basically a colloquial term for multiply substituted isotopologues. You can imagine that that correct name quickly gave way to the clumped isotopes terminology, which is much easier to use. But basically, we're looking at the distribution of isotopes in molecules. So you can easily see that at this very simple example here of a hydrogen molecule that can have either hydrogen or deuterium isotopes. And basically, where's my mouse? The normal version, the version that's most common would be the molecule with the two light isotopes, the two hydrogens. Then we have two single substituted versions here in this equation. And then we have the clumped species, the one that has two rare isotopes, two heavy isotopes in the same molecule. So this is what we're looking for. We're looking for molecules that have multiple rare isotopes in the same molecule, because the abundance of these is temperature dependent. And that's what we can use as a proxy. I won't go into much detail, but just very briefly, the reason why this is temperature dependent is the change in the 0-point energy of the bonds with substitution. So if we look at this zoomed in version of the Morse potential plot, we see that the 0-point energy for the hydrogen molecule is, or the 0-point energy for the doubly substituted one is lower than for the hydrogen, the two hydrogen molecule. And because of that, this bond is more stable or more difficult to break. And this characteristic comes especially into play the colder the temperature gets. So if we move now to a molecule that's a bit closer to our heart, to the CO2 molecule, you can actually model the effect, the temperature dependence of the abundance of these multiply substituted isotopologues with temperature, which is what you see in this plot. It's maybe slightly complicated. Sorry, I'm still looking for my mouse. So in this plot, I'll walk you through this. In this plot, you see on the x-axis temperature. So cold is on the right and hot, really hot is on the left. And on the y-axis, you have this capital delta in per mil. The capital delta is basically the overabundance of a given isotopologue compared to a stochastic expectation. So the larger this capital delta is, the more of those multiply substituted species you have in your material compared to what you would expect if everything was just randomly distributed. Of course, you always have by random chance molecules that contain multiple rare isotopes. But what we're looking for is an overabundance of these multiple substitutions. So in the case of CO2, you have different versions of multiply substituted isotopologues. You have the most extreme case where you have a CO2 molecules that contains just rare isotopes, so 13C, 18O, and 18O. This overabundance of this species is hugely temperature dependent. And then you have other species where there's maybe only one, sorry, not one, of course, that would be singly substituted, but where you basically have two rare isotopes in one molecule, like the 16O, 13C, 18O molecule. And the temperature dependence of this clumping here is a bit less extreme than when you have basically two bonds with two heavy isotopes. So in terms of a proxy for temperature, the one that we would be most tempted to measure, just based on this plot, would be the one that has the largest temperature dependence, obviously. But there's another thing to consider, the abundance of those isotopologues. So it has to be feasible to be able to measure those. And that's why you have this insert plot here that tells us the abundance of these isotopologues of CO2. And we see that, and this is a logarithmic scale, you see the non-substituted one in gray and then the single substituted ones in black. And all the doubly or multiply substituted isotopologues are much rarer than the ones we typically look at. So because of this, we, at the moment at least, have no chance of measuring this triply substituted isotopologue. We have to contend with the ones that are abundant enough that we can still measure them. And that is, for the most part, the one that contains a 13C and an 18O. So that's both abundant enough that we can just about measure it, and it has still a significant temperature dependence in this clumping state. So if we look at carbonate molecules now, we again have an equation here with different versions of the carbonate molecule, and we have one clumped version in here. Just a little self-test. Can just everyone identify the clumped version? That's this one here. So it's the version that has both a 13C and an 18O in the same molecule. And we are looking in speleothems and in other types of carbonates, we're looking at this, the abundance of this isotopologue compared to what we would expect if everything was randomly distributed. So just to drive this point home, what I realize often is that it's a bit confusing at first to think about isotopes in this way compared to the more classical approaches where we measure delta 18O, for example. So I just want to quickly explain the difference one more time. So with the classical isotope methods, let's say delta 18O and delta 13C measurements, we look at the relative abundance of the rare heavy isotope versus the more abundant light isotopes, right? So we ask the question, how much 18O do I have in my sample compared to 16O, right? And that is a function of the isotopic composition of the water from which this carbonate grew and temperature. And of course, the isotopic composition of the water, especially in our field here with speleothems, can have all sorts of other influences. And Matt gave a really nice lecture on that. But basically, we have these two influences on the delta 18O signal, the isotopic composition of the water and temperature. So if we were out for a temperature proxy, we have the problem that we don't have enough constraints often. Whereas with clumped isotopes, here, we're not looking at the abundance of the isotopes, but we're looking at the distribution of the isotopes in the molecules. So the advantage of this method is that we have all the information we need in our sample itself. We don't need to know what the composition of the water was. It doesn't matter for this proxy. And the distribution of the isotopes in this sample itself is a function of temperature. So we have temperature as the one control on the signal. It is in speleothems, this sounds all very straightforward. It is a little bit more complicated because what I just said depends on the system being in isotopic equilibrium. And that, as I'll get back to, is especially in speleothems, not always the case. So there is a bit more complication than this simple schematic here makes you think. But I did want to point out what the difference is between this clumping or isotope ordering and the isotope abundances that we are normally more used to thinking about. So just briefly how we determine isotope clumping. I said we have all the information we need in our sample itself. So what we do is basically almost the same as what we do for a normal delta 18O measurement. We dissolve our carbonate powder usually with phosphoric acid. We get CO2. From that, we have to do some extra purification steps, but that's relatively straightforward. And then we measure it in the mass spectrometer like we do for delta 18O. And we measure the same masses as for delta 18O plus one more. So we measure mass 44, 45, and 46, which gives us information about how much 13C and how much 18O we have in the sample. And the only difference is that in addition, we also measure mass 47, because that's the CO2 molecule that contains both of the rare isotopes. It's very, very rare, this doubly substituted CO2. So we do have to measure more precisely and measure for longer times. So it's a more involved measurement in a way, but in principle, it's a very, very close to what we normally do for delta 18O. So with each measurement, we do get the delta 13C and delta 18O information, and then we get information on the abundance of this mass 47. And together, we calculate the overabundance of the mass 47. So we measure how much 13C we have in our sample, how much 18O we have in our sample. From that, we can calculate just by random chance how often we would expect those to occur in the same molecule. So to give us mass 47, that's our random mass 47 signal. And then we compare that to what we measure actually is the case in the sample. So that gives us this capital delta 47, which is basically the ratio of the measured mass 47 abundance compared to what we calculate as a random occurrence of this mass. And we report that in the normal delta notation. So I don't want to go into more details here for the method part, but I did want to mention quickly that this has applications in very many fields of earth science, so not just speleothem science. And because of that, it's received quite a lot of interest in earth science community. So we can look at past climates, which is what I mostly do and what people here probably mostly do, but we can also use it to reconstruct mountain uplift or alteration of rocks beneath the surface. All of reservoir conditions, even climate on Mars has been studied with this, with Martian meteorites, or biological questions like body temperatures of dinosaurs by analyzing teeth of dinosaurs. And the first use of the method was actually in atmospheric science to distinguish CO2 that comes from combustion, from engines, compared to natural CO2, because you have different temperatures during the generation. Okay, but back to our interest here. So the challenges, the analytical or methodological challenges are, as I said, that the concentrations of those doubly substituted species are really small. So we have to do very precise measurements and have to repeat them many, many times to be sure about the signal. And in addition to that, the temperature sensitivity is actually quite weak. So we have only 0.004 per mil in our signal per degree Celsius. So we have to do those measurements precisely. And if that wasn't enough, we also have artifacts that can happen during the measurements that we have to constrain with lots of standard measurements of different standards of different composition. I won't go into that here today, but that's a whole other topic by itself, how we actually use the standards to correct for mass spectrometer artifacts. And then what is the topic for today is, as I said, disequilibrium effects that can strongly affect the clumped isotope signal. Just one plot to show you what I mean with many replicate measurements or why that's important. This figure shows the clumped isotope, the standard error of the mean of a clumped isotope measurement done on carbonate standards, in this case, 4 different ones. That's the 4 different colors. And you see the standard error of the mean with the number of replicates, that the number of repetitions of measurements for each of those. And you see that the stippled line is the 2 degree, roughly 2 degree error. So you see that in order to get the error down of each measurement to something useful for paleoclimate, we do have to do something like 20, 30 or so replicate measurements of the same material over and over in order for this to become useful. At some point, adding more measurements doesn't really help us anymore, unfortunately. But I mean, this is both maybe a challenge because we need lots of material and we need long measurements time, but it's also, of course, an opportunity because we know that the error mainly comes from this counting statistics. So if we have enough material and enough time, then we can beat down the error with replication. So I see this also a bit as a strength of the method. And then, so once we have all these replicate measurements, we've done the standard correction that I'm not going to go into today. We have our corrected capital delta 47 signal, and then we want to, of course, translate that into temperature. And for that, we use an empirical calibration. In the early days of the method, so the first calibration came out in 2006. It was very simple, a few natural carbonates, a few synthetic carbonates, and gave this calibration. I don't want to hide that in the years following that, I would say the last 10 years or so, maybe the clumped isotope community has struggled with then more and more labs coming online and deriving different calibrations. So there's been a long period of time where there's been a bit of a calibration chaos, if you want, with different labs working with slightly different analytical setups and working on different materials, deriving each their own calibration, some of them different calibrations for different materials in the same lab, that did not agree. So that was basically a time where you could pick and choose your calibration and get a very different temperature record from that, which is of course not satisfying. I am speaking in past tense here because I would claim that the community has overcome this stage finally. So we have worked very intensely on standardization, so on deriving carbonate standards that can be used by all the labs. That has helped a lot, and also by figuring out which correction parameters exactly to use, for example, for correcting for 17O abundance, and so on. So the situation is quite different now from just 5 years or 6 years ago. This is just one example of a calibration study where they compile lots of results from different labs on different materials, and you see that over a huge temperature range, so 1,000 degrees temperature, these results all agree really well and result in one calibration. So I would say that that's the status where we're at now, that we can derive calibrations that agree across different labs and across many different types of materials, if they are precipitated in equilibrium, of course. You might notice that the orange symbols here, no, you can't see that, but this is a calibration that's done on travertines. So that's quite close already to speleothems. And the travertines that were used for this calibration agree really well with other materials that are in part fossils or synthetic materials from the lab. So just to sum up the method part, clumped isotope thermometry has really big potential in many fields of earth science, because we are not limited anymore by having to know the isotopic composition of water for deriving temperatures. But it's a method that is analytically challenging and takes a lot of time. And the ongoing work in the community is still to minimize sample amounts, improve correction schemes. I would say we have made big steps in that direction, but we're still continuing to work on that. We're still trying to find out if some materials need different calibrations. There's not many, but there's a few types of materials where this seems to be the case. And then especially relevant for speleothems is this equilibrium versus disequilibrium effects. So let me see how much time I have. So to move to speleothem applications, I want to start with the first application that was done when this method was still very fresh. There was a lot of excitement about applying this to speleothems and getting this direct temperature information. And the first study was unfortunately a bit sobering in that respect. This was done by Hagit Afek and others. And they used studied Surrek cave speleothems for that. But very disappointingly, the temperatures that they got from last glacial maximum to Holocene samples were all way too warm based on the knowledge they had of the sample and the cave. So this very clearly showed early on that speleothems can be affected by disequilibrium effects. What Hagit and others did back then was that they basically calibrated with modern day samples and found an 8-degree offset. So they applied this 8-degree offsets to all their samples. But now we're a bit more advanced than that. We have different ways of dealing with these disequilibrium effects. But this was basically kind of the first downer in a way for application to speleothem science. The reason why we have disequilibrium effects here, I think you've probably heard quite a bit about disequilibrium and for oxygen isotopes already. So I'll just mention this briefly, but we do have the effect of CO2 degassing from the solution. And then, so we have exchange of CO2 between the solution and the cave air. And then we have the hydration and hydroxylation reactions between bicarbonate in the solution and CO2. Then we have kinetics that occur during the actual precipitation of carbonate, and we can have isotope effects during evaporation of water. So all of these processes have isotopic effects. And if they're not in equilibrium, if there's not enough time, say, from when the CO2 is degassing to when the calcite is precipitating for the system to get back into equilibrium, then the precipitated calcite will remember the disequilibrium that occurred during the CO2 degassing. And that's apparently quite often the case in speleothems. I do want to also point out, though, that in some occasions, in special cases, we find speleothems that are perfectly in line with other materials, so that do precipitate in equilibrium. Just as an example, this is a study that came out this year. It was a study on bivalves, so a very different type of carbonates, but they show that the two speleothem samples from very slow growing immersed speleothems, so Devil's Hole and Laghetto Basso, they fit perfectly with the line that goes through all the biogenic carbonates, forams and bivalves and other materials. So we do have in those special occasions speleothems that do precipitate in equilibrium. But those are special situations, unfortunately. Also, quite early studies have found that the disequilibrium, the amount of disequilibrium scales between the effect you see in the clumped isotopes and the effect you see in oxygen isotopes. And this has given some hope again that we will be able to correct for these disequilibrium effects. So this is a study by Mathieu and Dalleron, where they worked on all sorts of modern speleothem materials, different types of speleothems, and they found that the different types are differently offset. So they have different disequilibrium extent offset from zero, basically. So that in the zero corner, you would be with your expected with your known temperature, your expected clumped and oxygen isotope signals. So the different materials are offset to different degrees, but there seems to be a linear relationship between the signal in clumped on the y-axis and the signal in delta 18O on the x-axis. So they propose that you could use this linear relationship to back correct if you have information on both of those systems. So what they did, for example, in a later study by Karin Weiner, they measured oxygen isotopes, not just in the calcite, but also in fluid inclusion. So to have the oxygen calcite water disequilibrium and clumped isotopes in the same sample. And then they used the slope that was determined based on modern day samples that I just showed you to backtrack where those samples would sit in this clumped isotope versus oxygen isotope space, where they would sit if they had precipitated in equilibrium. And that seemed to work pretty well. But of course, the big assumption here is that this relationship between the two effects is linear and stays the same over time. And there are indications that this relationship between the disequilibrium effects on clumped isotopes and oxygen isotopes may actually be temperature sensitive itself, which then of course complicates things. So this is a figure also from a study, a very recent study that was using synthetic carbonates grown in the lab at different conditions. So that's the color dots here, but also results from previous empirical studies using cave samples. And it's basically showing you the slope of this relationship of clumped versus delta 18O with temperature. So it looks like there might be a temperature dependent on this slope, which will then make it, of course, more difficult to use that slope to back correct these disequilibrium effects in older samples. We have looked at samples that don't have much of such an effect, though. So there seem to be places where disequilibrium effects are relatively minor. One of those places seems to be Borneo, where we did a proxy comparison study a few years ago, and we compared clumped isotopes with 3 different fluid inclusion-based thermometers. And what we found, this was a sample that covered 3, so a glacial, an interglacial, and another glacial state, almost 2 glacial cycles. So marine isotope stage 11 and marine isotope stage 9. And what you see here is the temperature proxy, the 4 different temperature proxies in the colored symbols. You see this glacial, interglacial, glacial, and interglacial temperature evolution. I also plotted the calcite delta 18O that doesn't show the glacial interglacial difference, but that's a different story. But what I wanted to just show this for is that the green symbols, the clumped isotope temperatures, they agree actually quite well with the other proxies. I mean, there's of course scatter in all of them, and the errors are relatively large, but overall the temperatures are actually quite close to the other, what we get with the other proxies. And also for 2 recent materials, the measured cave temperature is the gray line here. The clumped isotope temperatures weren't too far off. So there seem to be cases where clumped isotopes might work relatively directly, although I also need to point out that it depends quite a lot on which calibration you use. So for those results, we were using a calibration we made in the lab based on very slow precipitation of calcite in the lab. And with that slow precipitation method, we could get temperatures that are that agree with the other proxies. But if we had used a more normal calibration, like the ones that I just showed you that agree with forams and other biogenic carbonates, the temperatures would have been 4 or 5 degrees warmer. So in disequilibrium. And because of that, it seems almost like we might need a separate calibration for speleothems. At least that's one approach that also Hagit and her group have followed. What they did a few years ago was that they tried to precipitate calcite in a way that's most similar to what we think happens during speleothem precipitation. They precipitated calcite at the surface of a solution, so it's in close contact with the atmosphere. And they derived a calibration both for clumped and for oxygen isotopes that's different in slope from basically the more established calibrations at that time. Interestingly, the delta 18O calibration that they derived is quite similar to the Tremaine et al. Calibration based on speleothems, on modern day speleothems that many use in the speleothem community. So this is promising, I would say, in that if we can somehow resemble the processes in the cave in those kind of lab experiments, that we can derive a calibration that is applicable to speleothems. And Hagit and these guys very recently used this calibration with Surrek. So they revisited the Surrek speleothems that this whole story started with, and used this surface precipitate calibration and derived temperatures that seem to make a lot more sense than those earlier results. So the overall absolute temperatures are quite close to what you would expect, and you see two interglacials with a glacial, variable glacial period in between. They compared their results, which are the blue symbols here, with SST, so sea surface temperature constraints from the Mediterranean in those colored symbols, and also fluid inclusion-based constraints from the same sample in green, and showed that the temperatures they derived with this calibration actually seem quite close to expectations. So I would say that's a promising direction in our field. Another promising new development is that Wayfu and others have recently tried to model the effects on clumped isotopes, but also on other isotopic species of these different processes during speleothem formation and the different disequilibrium processes, and got quite interesting results. I see that I'm running a bit late already, so I'm going to try and not spend too much time on this. So read up in the paper if you're interested. But basically, what is great is that they were able to show how these disequilibrium effects evolve over time in such a system where you start degassing CO2 and then exchanging in the DIC system. So basically, and the different colors here just mean that they change the conditions a little bit, but you basically see this evolution of the disequilibrium effect over time that then has a peak and then subsides again. And the same for clumped isotopes. So here, this is clumped isotopes just for carbonate, not for CO2. So that's why it's capital delta 63. But again, you have the kind of a peak isotope effect of this disequilibrium. But then when the system evolves further, you kind of go back to a different state. And if you combine now the clumped and the delta 18O effects into one plot, so if you plot those against each other, you can see this time evolution going in one direction. So this is basically the slope that also Mathieu Daron and these guys have found in the caves, that you have a linear relationship between delta 18O effects and clumped isotope effects at the beginning, but then the system basically moves around. So if you get back towards equilibrium, you then get back to your starting point again. So this is great because we can actually model this slope, but it also means that you could have systems where you're just too far evolved in this process that this slope is not applicable anymore. So it's also it shows a little bit the danger with assuming one constant relationship between those effects. Just briefly, they also compile lots of speleothem samples, natural speleothem samples, and basically showed that they're not way off with their model. That's basically what I take away from this plot. But what's more exciting is that the recent study by Tobias Kluge and his group showed with these lab precipitates that they made that they could replicate those model simulations. So basically the orange symbols are what they measure in the lab, and the green stippled line is what the model would predict in terms of evolution with time of these systems. And I think this is very promising and reassuring that you can actually reproduce those signals in the lab. There's of course still lots of uncertainties, but this is a promising direction. And just at the very end, I just want to point out that another promising direction is to not only combine clumped isotopes with oxygen isotope effects, but also within the realm of clumped isotopes, there's another species that the first labs have now started to measure, and that's what gives us the mass of 48. So we can measure mass 47, which is C13 and O18, but we can also measure mass 48, which is 2 O18s and 1 C12. So we have two different versions of doubly substituted isotopologues that we can both measure, and that have slightly different isotope effects. So this is, oh no, sorry. This is showing you the model predictions again from this model of Wayfu Guo, and then two speleothems on top of that seem to suggest that the model is not completely off. And again, we have kind of a direction that we can predict that those two effects would take with disequilibrium, and we can use that to back correct and derive non-disequilibrium affected temperatures. Okay, and with that, I just want to sum up that especially for clumped isotopes and speleothems, kinetic fractionation effects can strongly affect the signal. This is both a challenge, but also a strength, because that means that we can use clumped isotopes also as a disequilibrium indicator because it is so sensitive. And there's hope, I would say, for correcting those effects and tracing back the growth temperatures by either using the combination with oxygen isotope effects that requires that we have some knowledge on oxygen isotopes in water, like fluid inclusion measurements, and or by combining the different versions of isotopologues, mass 47 and 48. And what I didn't have time to go into here, but it seems like the extent of prior calcite precipitation seems to be a major factor for how much out of equilibrium a sample is. And so also knowledge on prior calcite precipitation conditions in the cave will help constrain this. Or if you turn it around, clumped isotopes might be another way of looking at how much prior calcite precipitation you have in the cave. And yeah, I think I'll leave you with the ongoing work so that we have some time for questions. Thanks for your attention.